Okay, class. So I'll use this particular lecture to complete the rest of chapter 4, keeping in mind that our objectives that we've covered so far is everything above the orange line, and the rest of this lecture will be focused on everything below the orange line. And so we've started classifying polymer molecules, and I mentioned that these can be differentiated based on their chemistry, their size or molecular weight, the shape, and their structure. And then if we look at these structures overall, those can be subdivided based on what we call isomers, which is what we'll cover today. So far we've done the differences in repeat units, of which you're supposed to know 5. And we've talked about the difference in size and molecular weight, where we've talked about things like, excuse me, your degree of polymerization, your number average molecular weight, as well as your weight average molecular weight. And so as far as shape is concerned, if we were to remind ourselves that our polymers have sort of a carbon-carbon backbone, as seen here, and if we're to look at each carbon atom, remember your carbon atom can have 4 bonds, and your polymer bonds or your covalent bonds specifically are um, non-directional. They're directional, and they're directional in the sense that around each carbon you have these sort of a tetrahedral structure that looks like similar to a camera tripod. And so if you take the first carbon in your backbone, the next carbon can be connected anywhere on that tripod. So you can have another carbon in that direction. And if you look at the second carbon, the opportunity for bonds, if you think about this first leg here as the top part of your camera, like I mentioned, the whole tripod thing. So this is the top of your camera tripod, and this circle here shows the region where you can have a carbon bond. So your carbon could be bonded here, or here, or here, or here, or anywhere basically in this cone. And so you might have a nice structure like this where your carbon your backbone basically follows sort of a zigzag motion, right, as you can see from this shape. Okay, or you might have something that's a little bit more messy where your carbon doesn't necessarily follow a zigzag motion, but it follows sort of a disordered motion. And so you have sort of a backbone that looks more like this. Okay, and so this is just basically possibilities in terms of the different shapes you might have for an extremely long polymer. And so depending on how long your chain is, you might have structures that are not neat like this, but sort of have this entangled polymer shape. Okay, and the way you can think of this is like similar to a shoelace or like spaghetti, where basically if you were to take one of the strings out, or if you were to pull one string out, you would basically have a longer chain in comparison to what you would see if all those chains were curled up. And this actually works well, and the way we would define this is sort of defining that polymer chain as being elastic. And what this allows is basically, if you were to apply a stress to that particular polymer, what that stress that you apply to it, or that load you apply to that material, will basically go into um, loosening this polymer. Similar to, again, if I mentioned the whole spaghetti thing. So if you look up here at this illustration, you can see basically that if I start to put energy into the system when it's all knotted up, that energy is going to go into releasing or pulling out that string until it's tight, and then maybe it breaks or something like that. And so in this sense, where you see where it mentions that mechanical and thermal properties depend on the ability of this chain to uncoil, basically if you have something like this where if you were to apply a stress, how much stress that material or that polymer chain can handle is going to be based on how well it would go from something like this blue curls to this black long chain. All right, so if you have any things inside your molecule that stop it from rotating or from stretching, so if you have bonds, for instance, that are rigid, then you would be able to handle a lot less stress, because you would not get this material or this chain going from this particular shape to that. And so you can think of this as one of the things that also differentiates your polymers as well. So we started with the repeat units, and then we talked about the molecular weight. And then if you think about the shape itself, that shape goes a long way into determining whether your material is going to be able to handle a lot of mechanical or thermal stress or less of that. Okay, and so just like I talked about load, you can think of its ability to handle a thermal load or a high change in temperature is also going to be based on how well it can go from this entangled shape to something that loosens it up. The fourth descriptor we can talk about, the fourth type of classification, is based on the structure of the polymer chain. So broadly speaking, we can divide this into four. Okay, so this A here is linear. This is branched based on the fact that you have branches. This is cross-linked, and this final one is networked. Each of these yellow dots represents a repeat unit. And so one of the things I talked about in class is that between or within the chain, okay, so each of these repeat units are bonded by a covalent bond, right? Because we said that the backbone for these are carbon. So you have carbon chains in the middle, and then you have your attachments to your carbon chain. And so basically what holds a chain together are your covalent bonds. On the other hand, between the chains, what you have is your van der Waals or your secondary bonds. And so the bonds within the chain are really strong, and the bonds between the chains are weaker. Same thing if you were to look at these, for instance, the bonds within the branches are covalent, while the bonds between branches are secondary. If you look at this third one where it's cross-linked, you actually see that everything here is covalently bonded. So you have this chain which is covalently bonded to this chain, which is then covalently bonded to this, and so on and so forth. So you would expect that this also has secondary bonding, but really what holds these individual chains together are the covalent bonds. So while here you have mostly secondary bonds between the chains, down here for C, for instance, what you would see is that you have both covalent bonds in the chain and also covalent bonds between chains as well. And for your networked, they're all covalent. And what we'll learn later on is that for A and B, they're going to have different thermal properties in comparison to C and D. If you think back to what I talked about in the previous slide, right? The ability for something to be able to handle thermal stress is going to be based on how well it can go from something that's entangled to something that's not entangled. And so when we talk about thermal properties, you're going to see that these linear and branched chains exhibit different properties than these cross-linked and networked chains as well. So now if we dive a little bit deeper into these general molecular structures, we come up with a term called isomerism. And I'll talk briefly about what that actually means. So if you think about what the word iso means, iso, right, is I don't know if it's Greek or Latin, but iso means same. So if you've heard of isothermal or isobaric or isochoric, for instance, so isothermal meaning same temperature, isobaric meaning same or similar pressures, isochoric meaning same or similar um, um, volumes. So unlike in basketball where ISO means isolation play, in chemistry when we say ISO, we're talking about something with similar structures. So let's look at, and remember the word mirror there is repeat units. So let's look at this particular structure here, for instance. So if I were to write down the molecular formula for this molecule on the left, it would be 8 carbons. Okay, 1, 2, 3, 4, 5, 6, 7, 8 carbons, and then 18 hydrogens attached to that. And if I had to look at this molecule here on the right hand side, which is this, it would also be C8H18. So 8 carbons, 1, 2, 3, 4, 5, 6, 7, 8, and 18 hydrogens. So these two have the same exact formula, and we would say that they pretty much have the same repeat units in a sense, because we still have we have carbon-carbon bonds, but the structures are different, right? This one, all my carbons are present in the backbone. In this case, I have carbons, like 5 carbons, well, technically, in chemistry terms, we have 1, 2, 3, 4, 5, 6. We have 6 carbons in the main backbone, and then we have 2 CH3s hanging off of that backbone. And so these have 2 different structures. So when we have materials or molecules with the same formula, So that's where the iso comes from, because the formulas are the same, but the structures are different. We would call those isomers. And for the purposes of this class, we're going to talk about two types of isomers. One type are stereoisomers, and the other kind are geometrical isomers. And we'll talk about both of those in the context of things you need to be able to recognize and know. And there are different times when you're going to see them. So let's start off with stereoisomers. And typically, when we're describing stereoisomers, so stereos at this point are probably like a relic from the 80s or the 90s. But if you think about a stereo, right? If you've watched, I don't remember what that John Cusack movie was called, but where he held a radio above his head and he was playing music to a girl in the window. You would recall that he was holding a radio and there were two speakers on that radio. That's what a stereo is. So a stereo really, and I think this comes from audio engineers as well. Your stereo is basically you have two sides, two speakers or two channels for your sound to come out of. Right, the opposite of a stereo is mono, where you only have things coming out of one channel. So the stereo here, or stereoisomers here, the way we can start describing this by looking at your left and your right hand. So your left and your right hand, if you notice, are mirror images of each other. Okay, so let me find my mouse here. Right, this is your mirror. Okay, so this is your left hand and your right hand, and they're exactly mirrors of each other, mirror images of each other. But you cannot superimpose your left and your right hand on top of each other. So if your palms are both facing you, you can't superimpose your left and your right hand, as shown in this picture here. Okay, and if your hands are, if the back of your hands are facing you, you cannot superimpose them on each other as well. I mean, sure, you can, if you put your palm for your left hand or your right hand facing you, and then the back of your left hand facing you, yes, you can superimpose them, but that would not be the point. The point here is that these two mirror images that you have, where your palms are facing you, you cannot take these two mirror images and superimpose them on each other. Okay, but you can see that the connection for your left and right hand are the same. You have your thumb, and then you have your index, your middle, your ring, and your pinky, right, on this side. And again, the order is the same here. So you still have your pinky next to your ring, next to your middle, next to your index, and next to your thumb. So the order is the same, right, in terms of the connections, but these are two images that you cannot superimpose on each other. If we're to take this to the idea of molecules, you can see here that we have a carbon in the middle, and it has its 4 bonds, one to fluorine, one to chlorine, one to iodine, and one to hydrogen, and the mirror image would look like this. Okay, and again, what you will notice here, this is our 3-dimensional picture. So we have chlorine here, we have your carbon, you have your hydrogen, and you have your iodine. And what you'll see is that if I took this image here and I tried to superimpose it on that one, right, my molecules will not line up. So for instance, if I were to superimpose this on that, my iodine will be facing this way, where my iodine will come out here, my hydrogen will be on top of my chlorine will be on top of my hydrogen. No matter how you do it, if you take this image and try to superimpose it on this, there will be no way for them to lie directly on top of each other. And when we have that, what we're describing there is a stereoisomer. So the idea is that the order of linkages are the same. So here I have carbon to fluorine, chlorine, iodine, and hydrogen, but their spatial arrangement is different. Okay, so they're linked in the same order, but their spatial arrangement is different, such that they cannot be superimposed. So again, the idea here is that you can take a mirror image, okay, and they're linked to the same direction or the same order, but they cannot be superimposed on each other without separating individual units. So for instance, if you were to look at this, the only way your left and your right hand can be superimposed on each other if you were basically to rearrange your fingers, which we do not want you to do. Okay, don't try that at home. But basically that's the idea here. That the only way to get these to line up exactly on top of each other, excuse me, is to separate the individual units and break some bonds. Okay, so how does this relate back to the work that we're talking about in terms of polymers? But remember that I mentioned that our polymers will typically start with an unsaturated hydrocarbon, and then we convert that double bond to a single bond, and now we have our repeat units. And so the way we can tell that a polymer is going to have a stereoisomer is if we have a group on our repeat units that differs from the other three. Okay, so basically what we need to do in our repeat unit is have at least one carbon that has two different groups on it. Okay, that would be the way you would, if you're thinking of it in terms of simply looking at it. Stereoisomers would be a situation where we take a carbon, okay, and one of the carbons in the repeat unit has two different groups on it. So for instance, if this R here is an H, then it's not going to work. This R here has to be something different, and that would be the only way in which these can be considered. This thing would form a stereoisomer. So let's think about this within the context of the five industrial polymers that we talked about, the ones that you have to commit to memory. And we'll think about it in context of what this R group here could possibly be. So one of the ones you have to memorize is polyvinyl chloride, okay, or PVC, which is this first molecule or first repeat unit here. And what you notice is that we have two carbons, right? In the first carbon, we have two hydrogens on that, so that's not a good candidate. But in the second carbon, we have a hydrogen and a chlorine. So this chlorine here is different from this hydrogen, which then tells me that I can form a stereoisomer from this particular repeat unit. And in this case, I would say my R group, or the R. So the R in chemistry is very similar to like your X or Y or Z in math or algebra, where basically that X there represents some variable. So in chemistry, R is like our chemistry version of X in math. And so for PVC, or polyvinyl chloride, our R group is chlorine. This one here, if you look at this carbon, you can see that you have an H group here and a CH3 here. So because these two are different from each other, we would say that could form a stereoisomer. And this is the repeat unit for polypropylene, or PP, where our R group is CH3. And then if we were to look here, this C6H5 fragment or portion is different from the H, and therefore we have something that can form a stereoisomer as well, and that is polystyrene, or PS. Now, there are other types of repeat units like that you didn't have to memorize, for instance. So if we look at this last one here, where we have this C that still has two H's just like everything else. But if you look at the second carbon, it has a CH3 at the top and a COOCH3 at the bottom. So these are different from each other, and we can say that this is one that has two different R groups, okay? And so R1 would be CH3 and R2 would be C2H3O2. So these four candidates and others as well will be ones that we can say right off the bat, just by looking at the repeat unit, that we can actually form a stereoisomer. So now we're going to talk about the different names for these stereoisomers. Again, just keeping in mind that the way I can tell that a polymer is going to have a stereoisomer is by looking at my repeat unit and noticing that I have a group on there that is different. I have two different groups on at least one of my carbons. Okay, if I can have two different groups on at least one of my carbons, that means that I can form a stereoisomer. So like if we were to have these two C's where they had four different groups, for instance, we would know that that would definitely form a stereoisomer. All right, so in describing stereoisomerism in polymers, we use the word tacticity. Okay, and that the word tacticity there, or tactic, is how we're going to use, we're going to name our molecules. And so to be able to actually visualize this, I'm going to be switching back and forth between the slides and this website that I mentioned on the first day of class. Okay, so this website I mentioned on the first day of class, which I'll provide you guys with the link later. One thing I mentioned is that this website is really old. So it only works with Java, and only works with Java in Internet Explorer or Safari on Mac. So it doesn't work with Chrome or Firefox or Edge or any of those. All right, so if we're to navigate to this website, which the link is provided here, and I can give you guys that when we talk again in class, you'll go to your repeat unit and polymer structures, and we'll go to stereo and geometrical isomers. All right, so the one we're going to deal with here are the different types of the different kinds of stereoisomers. So first things first. Remember that we represent our polymers our repeat units in a two-dimensional representation when we draw them on paper. So if I were to draw my set of repeat units, then all my R groups are on the same side. Okay, so there's that word same again. We would say that that geometry there is one that exhibits what is known as an isotactic arrangement. So iso in the sense that all of my R groups are on the same side of the chain. So again, just remember that your R here is representative of these groups that are different from each other. Okay, so those are my R groups, and because they all lie on the same side of my two-dimensional representation, we would call that isotactic. And so if we're to represent this in 3 dimensions, what you will see is that basically you have your carbon backbone, and then all your R groups lie on one side of your axis. Okay, so that's 3-dimensional representation. And if we were to use something like polypropylene as an example, for instance, you can see that all my carbons, all my CH3s, where my CH3 is my R group for polypropylene, all my CH3s lie on one side. And so let's go back to that website and look at what isotactic looks like. So we're going to wait here for Java to load. Give it a moment here. All right. So this is the isotactic geometry for polyvinyl chloride, PVC, where my R group here is my chlorine. So if you're looking at this in 3 dimensions, what you will notice is what? All my chlorines lie on the same side. So if I was drawing this in 2D, what I would have is my C forming my backbone, and then I'll have Cl, all my Cl's on one side, and then I'll fill in the hydrogen. So what you will notice here is, again, looking through this, all your chlorines are on, basically, if we're looking at this axis, for instance, all my chlorines are on the right side of this axis that passes through, that goes into the screen. Okay, so that's an isotactic polymer. So the next kind of isomer is one where my R groups alternate along my backbone. So they alternate on each other. And again, remember that what we're doing is this is one repeat unit, this is another repeat unit, and this is another repeat unit, and so on and so forth. People sometimes get confused because they will write the R here when they're sketching this out, and then they'll put an R here, and then they'll put an R here, and then they mess up the order. So remember that you want to draw the repeat units, okay, as these blocks, and then make sure that your R within each repeat unit alternates. And so if we look at this in 3 dimensions, oh, I'm sorry, before I go on, the name for this one, where the R groups alternate on either side of the carbon-carbon backbone, is called a syndiotic isomer, okay, where your R groups alternate sides. So if we're to look at our 3-dimensional representation again, what we'll see is that when we look at that plane, our R groups are on either side, okay, and this is a representation of what that looks like for polypropylene, where you see your CH3 on this side in this first repeat unit, and then your CH3 on the opposing side in this second repeat unit, your CH3 on the opposing side in this third one, and CH3 on the opposing side in the fourth one. So again, you can see that those alternate sides. So let's go back to our website and click on syndiotic for PVC. And again, if we're to look through this plane, what you will see is that based on where our chlorine is, again, our plane is a carbon-carbon backbone. So let me orient this way and see if we can get this to work. And what you will see again here is that your chlorine alternates sides, right? So you have chlorine here, chlorine there, chlorine here, chlorine there. Okay, and again, you can go ahead and play around with this. So if we're drawing this in 2 dimensions, this would be what I would draw, right? I would have my C's through here, chlorine down here, chlorine up here, chlorine down here, chlorine up there, and so on and so forth. Okay, so we've looked at 2 representations now. One, isotactic, all my R's are on the same side, and then this one is syndiotic, where all my R's alternate sides. And then the last one is atactic. tactic, where basically there is no order to my R, so they don't alternate and they're not all on the same side. They don't alternate sides either. Okay, and what you see here is that as you will notice, I can't say that these are all on the same side, and I cannot say that they alternate either. Okay, so this fourth one here is out of order in comparison to this. If we were to show that in 3 dimensions, it would look something like that. Again, where again, if I were to do that axis, I would see that there's no order or symmetry really to my R groups, and this represents that. So you can see two CH3s down here, one CH3 up here, and one down here. Okay, and so if you keep in mind, if you're going to draw these to be able to show me that you have 3 different kinds, so to be able to show me you have 3 different isomers, you would need to draw at least 3 repeat units. Okay, you need to draw 3 repeat units to be able to show me that I have a syndiotactic or an atactic or an isotactic to show me the difference between those 3. So if we were to go back to our picture and click on atactic, what you will see here is again that if I were to use my carbon-carbon as my backbone, right, I have 2 on this side, 1 on this side, and 1 on this side. So it's not like if it was syndiotactic, you would expect this chlorine to be over here, right? If it was isotactic, you would expect this chlorine to be down here, but it's neither of those two. This is completely random, and that's why it's called atactic, okay? Where the A there means without, right? So just like asexual, or right, without gender, this would be the same thing here. So without staticity means atactic, okay? Or amorphous, right? Without a specific morphology, when we talk about crystallinity, for instance. Okay, so those are your stereoisomers, your different kinds of stereoisomers. The other class are what are known as geometric isomers. Okay, and your geometric isomers are found in polymers that have a double bond present within within their repeat units. Okay, so these aren't ones you have to memorize, but these aren't specifically isomer names that you have to know. But what you will notice here is that these here are polymer parts of a polymer, or repeat units of a polymer where I have a double bond. So that's how you can know whether if you're talking about a stereoisomer, I have all single bonds. Typically in my repeat units, or at least my carbon-carbon backbone is all single bonds. Okay, and for geometric isomers, my carbon-carbon backbone has double bonds present. And so the names for this are cis and trans. In your cis arrangement, excuse me, what you notice is that, so this here is my carbon-carbon backbone where my double bond resides. And so I have these 2 groups hanging off of that backbone. If we were to look here, this will be my carbon-carbon backbone. So you can look at the cis isomer as one where the groups that hang off of the carbon-carbon backbone are on the same side of each other. So CH3 and H are on the same side, and that is where that term cis comes from. So this is a cis isomer because my groups that hang off are on the same side. In this particular case, my groups that hang off of the main chain here, so my CH3 and H that hang off of the main backbone, are on opposing sides of each other. So we'll call that a trans isomer. Okay, so you can look at this in terms of whether it's the direction in which the chain follows, okay, or you can look at it in terms of the groups hanging off. So that's why on the bottom here I say that when the polymer chain continues on the same side before and after the double bond, that's a cis isomer. When the chain continues on opposing sides of the double bond, that is a trans isomer. So you can look at it in terms of the chain, or you can look at it in terms of the groups that hang off. So if we look at this in a 3-dimensional representation, let's look at the cis. What you will see here is that my chain, right, continues on the same side after my double bond in each of these cases. Okay, and my groups that hang off are on the same side as well. So this would be the cis isomer for this particular configuration. So let's go back and let's look at the cis isomer for polyisoprene. All right. So again, if we look at this in 3 dimensions, you will see, and that's where that picture that I showed you is from. So the groups that hang off of the double bond are on the same side, and that's a cis isomer. Okay, for our trans isomer, you will see that our polymer chain, okay, continues on the opposing side after the double bond. So we go up, see the double bond, and this goes up. So this is down on the side of the double bond, this is up on the side of the double bond, so you can tell that it's a trans. And if we're to look at this, or you can say that these groups here hang off on opposing sides of the double bond, so up and down, so that would be a trans isomer as well. So let's go back, look at what the trans isomer looks like, and again you can see what happens there, right? The groups that hang off in this case, the CH3 and the H are on opposing sides, up and down, above and below. This is the way you can think about it in terms of sides. So again, down here, my double bond is written here. This is below the double bond. This is above the double bond. So that makes it a trans isomer. So again, as always, I would encourage you to go to that website, the VMSC website, which I would use a lot more in the class. If we go back to the main page, you can see that some of the chapters, it's taking some time to load, but some of the chapters we're going to talk about in terms of like diffusion and dislocations, which is chapter 5. I'm going to come back to this website and show you guys some more images, but it's important that you yourself go and try this out. And again, critical to understand, this only works with Internet Explorer and Safari. Unfortunately, it's like going back to the dark ages, basically. All right, so play around with those to be able to visualize them, but really, again, remember that we draw 2-dimensional representations of this to simplify how they look. All right, so to recap, when we're describing our polymer molecules, we can look at them the differences in terms of the chemistry, which is the repeat units, in terms of their molecular weight, in terms of their shape and their structure. And when I started talking about structures, I mentioned that we generally have your linear, your branch, your cross-linked, and your network. This is just based on how the chains themselves interact with each other. But then if we look within a chain, our individual chains have these isomeric states, where we can have stereoisomers and geometrical isomers. Your stereoisomers are present in the repeat units where I have mainly single bonds. Okay, and for stereoisomers, what I'm looking for are, when I look at that repeat unit, I look at one of the carbons and see if it has 2 different groups on it. If within my repeat unit, one of my carbons has a different group on it, it's going to fall under one of these 3 types of stereoisomers. My geometrical isomers are present when in my polymer molecule I have a double bond present. If when you have a double bond present, that means you're going to possibly have a cis arrangement or a trans arrangement. Okay, and again, in your cis or trans, the groups that hang off of the double bond have to be they have to be one above and the other one below for you to be able to get that representation of a geometrical isomer. All right, so the next property of isomers we'll talk about, of polymers, we'll talk about our classifications based on the thermal properties of the polymer. Okay, so we can describe a polymer as being thermoplastic or thermosetting based on how it responds to temperature. And actually, I would say one of the ways I always remember this was something back in, I think it was high school, elementary school, where they talked about the difference between water bottles and buttons that are made for shirts or blouses. And so your thermoplastic polymers are polymers that basically when you heat them up, they soften, and when you cool them down, they harden. Like most materials, that's what happens with them. But basically with thermoplastic polymers, of course, when they harden, they can form a specific shape. But what happens is that when they soften, when we heat them up, they soften, and we can basically reshape them to form some other shape, and then harden them again and cool them down again to give a different shape. So the main property for your thermoplastic polymers are that you can basically, you can reshape them and make them into different shapes just by applying heat. And part of the reason for that, so some examples of that are your milk jugs, for instance, or like I said, water bottles. and things like that. So sometimes you see that there's some water bottles that you have which are plastic, and they will say not to wash them in a dishwasher, or wash them on the top level of a dishwasher. Because what you realize is that, and I've done this before, I put the water bottle, because I was lazy, I put the water bottle inside the dishwasher, and after it was done, it came out and it was a completely different shape than before because of how much heat we added to it. And part of the reason why is because these polymer structures have mostly secondary bonding within the chains, and so because the secondary bonds are weaker, once I apply some heat to them, those secondary bonds can be broken, and then we can rearrange these longer chains in some shape and cool it down, and they harden again. And so these thermoplastic polymers usually will have this shape where this is linear and this is branched. And again, the idea is that the application of heat allows the secondary bonds to break, which allows me to reshape these particular materials. On the other side of that are polymers that are known as thermosets or thermosetting polymers. And what that means is that when the material is still able to be shaped, so either it's a liquid or it's at least slightly viscous or thick or thickly flowing, you can reshape them, so you can form these polymers into any shape you want. But once they harden, you cannot reshape them anymore. Okay, and so like if you were to look at, for instance, your rubber tires or dice or your pool balls, those are ones that once they formed a specific shape, you cannot reshape them any longer. If you were to try to heat them up, basically what will happen is that you will continue to heat and heat and heat, and eventually they will burn, right? Those covalent bonds or those carbon bonds will be formed into carbon monoxide or carbon dioxide, and you release that. So these are ones that are not, you can't reshape them once you've set their shape, and that's where the word thermosetting is from. And part of the reason why is because your chains that you have, or your repeat units, are all covalently bonded. So rubber, for instance, has this type of structure, and then this is a phenol formaldehyde material, and that has this network type of structure. And what you see is that these are all covalent bonds. And remember what I said, just because a polymer has a lot of secondary bonding doesn't mean most of the bonds there are weak. If you have covalent bonds, your covalent bonds are really strong or relatively strong, and therefore you can't, when you heat these up, you don't break these bonds, right? These bonds are rigid, and so the only way to break them is to basically convert it to something else. And so your thermosets are polymers that do not respond to temperature, in the sense that you can't reshape them. Once they're set, that's it. Okay, so that's the main difference between thermoplasts and thermosets. And always just try to remember that those properties, just like in material science, the properties, those thermal properties, can be related back to the structure or the arrangement of these chains. Okay. The last thing we'll talk about is crystallinity for polymers. And so remember that the idea of crystallinity is that you have some structural or ordered structures, like we talked about with ceramics and with excuse me, with ceramics and with metals. Okay, so the question you might ask yourself is, well, when I have something like this where you have all this entanglement, right? Let me switch this to laser pointer. All right, when you have something like this where you have all this entanglements, how would you get any order, right, out of this, right? The only way to do that is you have to have these things sort of like lie or align across each other in some way, shape, or form. So let's look at an example. These this two structures here, okay, are structures of two types of polyethylene, or PE. Okay, so A here is one type, B here is another type. And our polyethylene can be described as being either a high density polyethylene or a low density polyethylene. Okay, and so if you were to ask yourself, if I were to look at this structure here and I were to look at this structure here, which of these would I define as high density and which of these would I define as low density? So let's just think this through. Think about what when we say something has a low density, right? So density is a function of mass right, divided by volume. So if two things have the same mass, right, if the volume is high, the density is low. If the volume is small, the density is going to be high. Something that has a low density is going to occupy a large volume, and something that has a high density is going to occupy a smaller volume. Or the way you can think about it is something that's high density is going to be tightly packed, right? It's going to be efficient in terms of space, and something that has a low density is going to be um, more spacious. So as to look at these, right, think about what happens if you were to like take twigs or branches, right? So imagine this is a tree branch that has like a lot of stuff hanging off of it, and this is a tree branch where most of the or a twig rather where most of the branches are cut off and it's mostly linear. These guys in your A and these guys in your B are going to lie very different from each other, and I want you to be thinking about that and think about how that has to do with density. So I'll give you a moment here to think that through, and then I'll explain what's going on. Okay, you can pause the video here. And so if you were to think about it, basically here, because I don't have a lot of stuff hanging off, I can put a whole bunch of these right next to each other. Okay. While for this one, I'm going to have less in the same space, right? I can't pack these tightly because there's a lot of stuff hanging off. Sometimes people look at this and think, well, this has a lot more branches, so therefore this must be high density. Well, the fact that this has a lot more branches has more to do with the mass than the volume. The fact that this is more spread out has to do with the volume part of this. So this is going to occupy more volume with less branches. This is going to be able to, this is going to occupy less volume. This is going to occupy more volume or take up more space. This is going to take up less space. And therefore, this would be your high density and this would be your low density arrangement. And if we were to look at the polymers or the properties, you will see that for high density polyethylene or HDPE, your density is in that range. And for low density HDPE, your density is in that range. So this is a little bit higher than that. But then look down here at your crystallinity, right? So the fact that I can pack more of the HDPE chains in there means that I'm going to have a little bit more crystallinity because I can have a little bit more order. While for your low density, I have a lot less order. And so if you think back to our metals and ceramics, our metals and ceramics typically have high densities because they make efficient use of their space, right? And so, or they have that non-directional bonding that we talked about. So in polymers, you can possibly have some crystallinity, but with polymers, it's impossible to have something that's 100% crystalline. There's going to be some arrangements where they can lie beside each other, but for the most part, most polymers are amorphous, and then sometimes in the case of high density polyethylene, as you saw, for instance, you can have some crystallinity to them. And so if we look at this under a microscope, and so that's why, again, because you have these really, really long chains, you have a lot more opportunities for these things to sort of entangle each other than to lie right by each other or lie next to each other. So if you were to look at a polymer under a microscope, you will see some regions that are crystalline, like where these kind of lie right beside each other, so there's some order to them. And then you have these regions here that are not crystalline or without morphology. So that's where the word amorphous is coming from. And so for the most part, polymers are rarely 100% crystalline, but they can have some crystallinity to them. And the reason why they're rarely 100% is because, again, due to these long chains, it's more likely that those chains are going to be entangled than become aligned. And finally, as I mentioned previously, these, if you ever looked at your bottles or your containers, you're going to see that they have some numbers obviously associated with them. So for instance, if I were to go back, right, we have 2 for HDP and we have 4 for low density or LDPE. Okay, so these numbers here that you see in your recycling, they give us a sense of the kind of material we have, and the goal is to be able to group these materials along the same line, and that will help with recycling. Now, I mentioned again that recycling is really difficult because even though all these different, so if I took all the ones, all of them will be all made of PET. The problem is that you have sometimes you have paint, right, on these materials, or maybe you added some pigmentation to them while you were making it. So like your water bottles, when you have your gray water bottle or your green water bottle, for instance, you've put in some color there to give that material some color, or to give it some, you've put some pigment in there, and your pigments are usually some inorganic material to give it some color, and so you have to separate all that out. So even though we can help the environment in general by trying to recycle polymers, there's some difficulty there because of how efficient the processes are, and basically just how much it costs. But that is why we're educating you and training you. You guys might be the ones to come up with the next idea to figure out how we can better improve our polymer recycling. All right. So with that said, again, this lecture covered the last set of these learning objectives. Okay, and I'm going to put up these slides on Microsoft Teams so you have them. But remember, for this chapter, these are the things you need to know. I'll see you guys when I get back. Make sure you study this well, and if you have any questions, we'll talk again in class. Thank you for your time, and enjoy your time off. Talk to you soon.